Welcome to Brain Vision.
Okay, this is question 5.112 with a moving wedge. So we have a wedge with mass big M sitting on a frictionless horizontal tabletop. And there's a block with mass little m sitting on the wedge. There's no friction between either the mass and the wedge or the wedge and the table. And then the system is released from rest. And in part A, we're asked to calculate the acceleration of the wedge and the horizontal and vertical components of the acceleration of the block. So let's just think about what's going to happen here. When we release this mass from rest, it's going to be pushing down on this wedge, and the wedge is going to be pushed, so it's going to accelerate in the minus x direction if we say that this is, the x direction is horizontal, because it can't move down at all. So it's going to be purely moving horizontally. So the acceleration will be purely in the minus x direction. And then this smaller mass is going to be moving down the wedge. The wedge is going to be moving backwards, so it's going to be not just one simple trajectory, but it's going to be pulled down by gravity, and it's also going to be moving, it'll be pushed by the slope of the wedge here. So we'll have three things that we want to solve for when we're talking about acceleration. So we'll have the pure acceleration of the wedge, and I'm going to just call that capital A. So let's think about the wedge first and set up the equation of motion for the wedge. So we're going to have the mass of the wedge times, I'm going to again say A is the horizontal acceleration of the wedge. And that's going to be minus n, because again, we're going backwards, so there's going to be a negative sign. And n is going to be the normal force between these two objects. So n is the normal force. And then since we only want this horizontal component, it's going to be multiplied by the sine of alpha, the sine of this angle. So that's our first equation of motion here. Now the second one, let's think about the x direction of this block. So I'm going to say, just call that ax, little ax. So m times ax is going to be, again, this will just be, this is Newton's third law. So this is going to be the opposite of this force, essentially. So it's just going to be n times the sine of alpha, but positive this time since the wedge is going to be pushing it to the right. And then we can think about the y direction. So in the y direction, we'll have the component of the normal force from in between these two blocks. So that's going to be n times cosine of alpha. And then we also just have gravity pulling it straight down. So that will just be m times b. So we have these three equations, and we want to solve for a, ax, and ay, but we don't know what n is. So we right now have three equations, but four unknown variables. So that's going to be impossible to solve. So one thing that we can do is think about if we take a look at these two equations. Like I said, n sine of alpha, this is negative the second equation. So we can set up, using these first two equations, we can say that m times a is negative m times ax. So this will let us say, for example, if we wanted to solve this for ax, equal to minus m over m times a over little m. So this is one thing that we can do to solve this. And one final thing, we're going to need one other separate equation here. What we can do is think about if you're just sitting at rest on this wedge, the horizontal acceleration of this block, remember this wedge is going to be moving with minus big A to the left, and this little block is going to be moving with acceleration little ax to the right. So the total horizontal acceleration of the block, I'll say horizontal acceleration will be ax minus capital A. And then the vertical acceleration, you only have one of those, is going to be ay. So we have vertical acceleration coming down, horizontal acceleration ax minus a. And we can set that, since we know that the block is going to be descending at this angle alpha, we can set up this equation ay over ax minus a is equal to minus, because it's going down, tangent of alpha. So this is going to be the fourth equation that we can use to solve this system of equations. And now it's just kind of a matter of doing some of the really messy algebra here, unfortunately. So let's start this. I'm not going to do everything out completely explicitly, but I'll sort of show one way that we could start approaching this. So let's use, for example, this equation here, our ax equals this here, to find n, since we definitely don't want to, we don't care about solving for little n, we want to get rid of it. We want to find ax, and ay. So let's start with this second equation over here. Just gonna, and then I'm gonna plug in this equation that we found just from combining these first two equations. So this is essentially, all we're doing is just plugging this in. And again, I just want to solve for n here. So these factors of little m are going to cancel out because we have m on top and n on the bottom. And we're just going to get that n is equal to this. And we actually could have just gotten this from rearranging this first equation too. So there are a lot of different ways that we can go about solving for all of these. There is no one right answer. But once we have, we've found n, for example, let's just go ahead and plug that into our equation for ay. So our strategy here is really just going to be to try to plug in as many things as we can, try to eliminate as many variables as we can to end up with just ax, and ay. So if we look at this, we have cosine divided by sine, and that's just 1 over tangent. So I'm just going to get rid of that and call this tangent of alpha here. So we have this. Now I'm going to come down to this final equation and just rearrange it a little bit. So I have ay is minus tangent of alpha. I'm just going to multiply both sides by this term here. So now we have this is equal to ay, and then this is also equal to ay if I divide by m. So I'm going to divide by m here. I'm going to call this over m tangent of alpha. Just be explicit here. When I divide by m, this factor is going to go away. So now I have this is equal to ay and this is equal to ay. So I'm going to bring this over here and set that equal to this on this side. Now, finally, now here's where I'm really going to use this one, where ax is equal to minus capital M, capital A over m. If I plug that in here, so my strategy right now is just to get, I want to solve for capital A. So I'm trying to plug in as many things to this to get capital A alone as I can. So now when I just plugged in for ax, I have all of these terms, and they're all in terms of just capital A. There's no ax or ay. So that's great, because that's going to let me, if I just simplify this, again, I'm not going to go through all of the algebra here, but I have a negative sign, which is going to cancel out all of these other negative signs here. This is just, now we have a plus here. I'm just going to distribute out this tangent sign over here. And then this is going to be equal on this side. So now what I can do is group these terms with a together and then solve for them. So this is just a matter of rearranging, and it's messy algebra, so I'm not going to explicitly go through all of that. But what we should get when we do this out is capital A is equal to mg, and then we should have m plus little m times the tangent of alpha plus m over tangent alpha. So this whole thing is in the denominator of this fraction. So now we want to get ax, for example. We can just plug this in. We now have big A, so we can just plug this entire thing in for this here, and then we'll get a factor of m on the bottom here. I guess I could do it. We'll have m here and an m in this term, and we can write that out a little bit nicer. So I'm just going to write out explicitly. This is the result of simplifying all of this. Is going to be capital M times G over, we're going to have the same denominator as before. So I'm just going to copy this here. So that's going to be our AX. And then finally, we want to find a Y. So again, we can, there's no one right way to do that. We could either plug into this equation for AY, that's probably the easiest, or we could use this one here where we know what N is. Either way, we can plug in and solve. I won't show all the algebra, but when we do that, we should get the numerator is going to be G times M plus little m times tangent of alpha. And then the denominator is going to be the same as all the other ones here. So this is all a bunch of kind of messy algebra, but we should end up with these three final equations. I'll just copy and highlight them down here so that it's clear what the final results are. So here's our final A of the block, AX of the wedge, and AY. I'm sorry, this is A of the wedge, AX of the block, and AY of the block. Now, part B says, do our answers to part A reduce the correct results when M is very large? Well, when M is very large, then we can basically say that this wedge is not going to move. So then we have this simple situation where little m is just going to be sliding down in the direction down along the wedge that this is kind of an example that we've solved for a lot of times before. So let's think about that. We want capital M to be much greater than little m. So in that case, let's see what happens when this, if big M is really, really big, then the denominator here is the denominator is proportional to big M both terms. So this is just going to go to 0 because we have basically infinity in the denominator here. So that's exactly what we expect. We have no acceleration of the wedge. Now, the acceleration of the x component here, we have an m in the numerator here. So that's no longer going to cancel and end up to 0. But if we take the limit here, as big M is basically going to infinity, then the limit of AX is going to be G times, G divided by, we're going to have this factor of big M. Sorry, let me just explicitly say this here. So we originally have this capital M in the denominator, but little m is much smaller than that. So we can basically say that little m is negligible or 0 compared to big M. And now we have big M in the numerator and in both terms in the denominator. So that's just going to totally cancel out. We're just going to be left with 1 over here. This is going to cancel. So this is what we're left with, which will simplify to G. If we just do out the trigonomic identities here, we'll end up with G sine of alpha cosine of alpha. And that's going to be the acceleration of the block, which makes sense here. Now, AY, we should have, remember, in this case, the acceleration is pretty much just going to be due to gravity and then slowed down by the y component of the normal force here. So if we do the same thing with AY, then we should end up with AY equal to minus G times sine squared, I guess I can just write it like this, sine of alpha squared. And that is going to be, again, what we expect because it's going to be related to just the force of gravity acting on this block with the normal force from the wedge. Now, part C asks us, as seen by a stationary observer, what is the shape of the trajectory of the block? So the trajectory of the block, remember, is going to be described by this equation and this equation, ax and ay. So it's a little bit tricky to see, but if you plot this out, you'll see that ax and ay actually give the trajectory of a spiral. So a spiral trajectory is the answer for part C.